Okay, so last time we ended with this discussion of the algebraic criterion for constructability. And so the idea was that these questions that have been asked for thousands of years about which precisely which things were constructible using compass and straight edge only. Um, this question, at least, was answerable in the negative, meaning that we could, uh, hypothetically, if we could show that certain numbers were not constructible or were not expressible as a finite sequence of certain operations, we could show that those things were not actually constructible with compass and straight edge. So what did I mean by that? So last time we gave description of what exactly was involved in being able to write in coordinate geometry equations of lines, equations of circles, equations of line, and equations of circles. This basically talking about this allowed us to find points as intersections of all those geometric objects that come from compass and straight edge. So I get lines from straight edge, circles from compass, and then I get points that I can draw in as part of these operations. So ultimately, what we deduced was that all we needed to construct all these things were the operations plus, minus, times, division, and radical. Okay, and of course, these four we constructed in our first chapter. The radical was something that actually we could do, that we did in chapter 2. This was part of what you did in your homework, how you can construct, say, the square root of some number. And so all these four operations were constructible with compass and straight edge. And it turns out that those are all you need. Okay, that anything that is going to be constructible has to be obtainable from the number one using these five operations. And so if we can show that some number is not obstructible in some finite sequence of moves from 1 using just these operations, then whatever geometric thing that I'm being asked to do is not possible with compass and straight edge alone. So maybe it's nice to give a few examples. So some examples. Doubling the cube. I know we haven't discussed much other. We discussed the platonic solids, the regular polyhedra, but we didn't go into three-dimensional Euclidean geometry, which is what Euclid does in the last bit of the elements that is saved for the three-dimensional stuff. So doubling the cube is a compass and straight edge construction in three-dimensional Euclidean geometry. It's exactly what it sounds like, i.e. Given a cube of some volume, constructing a cube of double the volume, okay, of the given cube. Okay. 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 So creating a creating a creating a cube of some volume given doubling the cube by doubling its apparent volume. So you're given some cube, you want to construct double that thing in volume. So what does this amount to doing? So in order, for instance, right, this is not the only thing that is required, but what would be required here? It's constructing the cubed root of 2. Okay, so constructing the cubed root of 2 is what I would need to do. So if I can show that the cubed root of 2 cannot be obtained from 1 in a finite number of steps using only these operations, then I'm done. Okay, I'm done. And what do I mean I'm done? It's impossible, right? So if cubed root of 2 cannot be obtained from the above operations, then doubling the cube is impossible. Using only compass and straight edge. Okay. Another example. For instance, squaring the circle. Okay. So before I mentioned squaring the circle, the reason the Greeks were driven to attempt to square the circle is the following. It is possible with compass and straight edge to square any other given polygon. So if you have an n-gon, you can square it. What does that mean? So it means to construct a square that has the same area as that given polygon. So one of your homework problems involves this. So one of your homework problems had you constructing a square that had the same area as a given rectangle. So you start out with some given rectangle. You want to construct a square that has the same area as that rectangle. So it turns out that you can actually do this for an n-gon generally. So if I give you a pentagon and ask you to do the same thing, you can actually do it. If I give you a hexagon, ask you to do the same thing, you can actually do it. So, and the Greeks knew this. Because of this, it might have been tempting to say, well, if I can square arbitrarily, larger polygons with arbitrarily many sides, then thinking of some ideal, polygon with like infinitely many sides, that's one, intuitive way of characterizing a circle or thinking of a circle. And so, in that case, right, it seems reasonable that I should be able to do this. So what would I need to do? It turns out this means I need to construct pi. Okay. Thus, if I can show that pi is not obtainable from 1 via those operations, then I can say that squaring the circle is impossible. Via compass and straight edge. Okay, so that's nice. One more example, trisecting the angle. Now, as I've mentioned before, there are some angles that can be trisected, okay, but there are others that can't. So the thing that would be needed in this case is, for instance, an angle of pi over 3. So pi over 3 is not trisectable. That's a funny word. So pi over 3 is not trisectable, and in order to show that pi over 3 is not trisectable, therefore a general angle is not trisectable, then what I would need to show is that cosine of pi over 9 is not constructible, and it's not. Okay. Now, unfortunately, we are not going to have the machinery to actually show any of these results. So all these things I mentioned are impossible. Okay, so doubling the cube is not possible. Squaring the circle is not possible. Trisecting a general angle, so specifically trisecting an angle of pi over 3 radians is not constructible. It's not doable via compass and straight edge. Okay, but actually showing these things, so showing that pi cannot be obtained from 1 via those operations, showing that cosine of pi over 9 can't be obtained from 1 via those operations. Same thing for cubed root of 2. That requires algebra that is going to be beyond the scope of us. So this, all of these results showing the impossibility of these things of the above constructions weren't proven until the 1800s, so more than 2,000 years later. Okay, so this was originally shown by I think it's Pierre Wansel. Okay. If you want to know what does it, in the event that you've actually had some algebra background, I'm not actually sure if this is the original way he did it. It might be, but one way of saying this is it's the multiplicativity formula of the degree of finite field extensions. So that might sound like a really, really complicated thing. It's not too bad. It's something that if you don't get to it in a 1-year course in undergraduate algebra, it's certainly something within reach, although I think you would get to it nonetheless. And actually the results after you see this are actually really straightforward and simple. So this is what was required to do that. And actually it pops out of, it doesn't seem to be related in any way. It's actually kind of miraculous that it gives you a solution in that way. Okay, all right. So this is tying this together with these questions of which things are constructible. It turns out these questions are really, really hard to answer. And like I said, it took algebraic machinery that didn't come around for another 2,000 years before these questions were able to be answered. Because, all these things were considered by the Greeks thousands of years ago. Next, I want to talk about angles, right? So we just spent that last little bit talking about which things now we can construct fully in coordinate geometry. So points, no problem, lines, circles, being able to find points that arise out of intersections of those things, all that's good. But now, other than those objects, another thing that we were very interested in Euclidean geometry is angle. Right? Now here's a potential issue, right? So note distance between points is expressible. Well, let's give ourselves 2 points. So let's give ourselves the points, say P1, which has coordinates x1, y1, and P sub 2, which has coordinates x sub 2, y sub 2. So distance between 2 points is expressible algebraically. What do I mean by that? So it means that it is expressible entirely in terms of those operations that I had listed previously. So it was entirely expressible in terms of, so the distance between P1 and P2 is square root of x sub 1 minus x sub 2 squared plus y sub 1 minus y sub 2 squared. Right. So when we say algebraically, we mean of a form like this. Now, I'm also going to include things like if this had to be nastier, it might still be an algebraic expression. But why am I making a distinction here? But this isn't the case for angles. Okay, So what do I mean? Well, the angle, say theta, between a line let's say y equals tx. So this is a line having slope t, and the x-axis we'll say. So here's my line y equals tx. Here's my x-axis. Here's the angle theta that I'm wanting to pick out. So the angle theta between a line y equals tx and the x-axis, okay, is, how do I compute that? How do I compute theta from this picture? So you might remember this, right? Theta is going to be, so the angle between y equals tx and x, theta is actually arctan of t. Okay. That is not algebraic, that's what we will say. Right? It involves some analytic function, something that you would study in a calculus class, that is more mysterious maybe inherently than something like this that's just addition, subtraction, multiplication, or exponentiation and roots. Right? This is something that's a little trickier, right? Even the inverse function, right, is tan t. That's again, you know, an analytic thing. This is something you find in like a calculus class. This is a little tricky. This would bring into focus all sorts of strange conundrums we would have to pay attention to, you know, very carefully, which is fine. That's perfectly fine. But we want to try to avoid that. So we want to try to keep everything algebraic for now because we're in the world of coordinate geometry. We're trying to keep everything in terms of the algebra that we're doing. So of course, this isn't just true of tan. This is true of sine and cosine as well. So any of those trig functions have this issue. So then how, this is a question, how can I keep the discussion of angles in the realm of algebra? Okay, the answer is I can use the slope and the notion of relative slope. Okay, now we're not going to spend that much time building this up. I'm basically going to define it and then tell you that all the stuff we want to come out of this comes out of this perfectly fine. So that's the approach I'm going to take. So I can use the slope and the notion of relative slope here to get what I want. So how do I define this? So let's say maybe I'll get myself a couple of different sheets of paper. So if line L sub 1 has slope t sub 1 and line L sub 2 has slope t sub 2, the slope of L sub 1 relative to L sub 2 is defined by the following. It is plus or minus the absolute value of t sub 1 minus t sub 2 divided by 1 plus t sub 1 times t sub 2. Okay. Okay. Where does this come from? So what is this? This comes from the following formula. that is the difference of angle formulas for tan. So tan of theta sub 1 minus theta sub 2 is tan of theta sub 1 minus tan of theta sub 2 divided by 1 plus tan of theta sub 1 times tan of theta sub 2. So note, if I replace each of these things with t sub 1 and t sub 2, I get exactly this formula, except for this absolute value plus minus business. So what's the deal with that? So why the plus minus sign and absolute value? All right. So okay, this comes from this weird formula coming from trig. So what about this? The only other difference here is plus minus sign and absolute value. If I have two lines, right? Let's say here's L sub 1 and here's L sub 2, right? And they cross, so we can talk about angles formed by these lines. What do you notice? There's an issue here, right? If all I have are lines and their slopes, okay, here these two lines cross, but if all I'm looking at is the slope, what angles am I even talking about? Right? If you're wanting to use this quantity to measure angles between two lines, if all you're talking about are lines and slopes of lines, then where in this picture does the angle come in? Well, that's the problem. It doesn't quite, right? And the reason it doesn't is because, am I talking about this? Am I talking about this angle? Now, once I specify those two angles, of course, vertical angles are congruent, so this is the picture I get. And so what do I get here? I get that using the relative slope, I don't pick out a single angle. I actually pick out a pair of angles that sum to pi, right? I get a pair of angles that sum to give me a straight angle. Okay, and so because of that, whatever I'm picking out here always has the issue of possibly reversing the sign. Okay, and that's why this is only defined up to this plus minus sign after I take the absolute value. So this ensures that the quantity that I'm dealing with is consistent and it's not ambiguous, right, which angle I'm choosing here. So this allows me to talk about angles between two lines in a sensible way without needing to bring tan into it directly. Okay, so what is the purpose? So we can use relative slope. We're not going to do this. It would take way too long. We can use relative slope to prove SAS and ASA and all of Euclid's and Hilbert's axioms. So this is the last thing we need, actually, as far as our coordinate geometry goes, and we can prove all of that stuff that we got in Euclid from this. We're not going to do it this way because there's another way we can do it. Now that we have coordinates, we have something else that we can do, although this is perfectly fine to do it this way, and it's important to see this. I may give you a homework, a problem for your next homework assignment that does this a little bit. That gives you like a couple of ways of considering relative slope here. Now, on to the thing that we are going to use to prove SAS and ASA. And it's actually the thing that Euclid did to prove these things, although the way he did it was a little hand-wavy. Although he certainly knew that it could be done this way. He just didn't develop it from the ground up like this. And that is the notion of isometries. So I have already brought this up previously. Isometries were what Euclid called rigid motions of the plane. Okay, and so when Euclid talks about motions of the plane, this is what he was discussing. we are going to mention over and over again the notion of isometries, because it turns out this notion is extremely important, because it is going to give us that last pillar of geometry. So if this textbook is 4 pillars of geometry, the last pillar, the 4th pillar, and the one that brings you into modern geometry is thinking about isometries on their own. So we are mostly going to think about them specifically related to the plane, and specifically for Euclidean geometry. So note that in Euclidean geometry, no point in the plane is special. And no line is special. What do I mean by special? I mean that any line in the Euclidean plane is the same as any other line. Any point in the Euclidean plane is the same as any other point, right? We're talking about lines now, not line segments. So any 2 lines are identical in a sense. So when Euclid talks about a line, he doesn't care if the line is over here or over here. In some sense, they are as lines separately. We're not talking about whether they intersect or whatever. As lines separately, they are treated as identical objects. Okay. So how can we reconcile that with coordinate geometry, right? Because in the coordinate plane, this is different, right? But in the coordinate plane, we have a particular point, a special point. So there is a special point, the origin. The origin is a preferred point, right? It is a preferred point, or a point that is singled out in some way. Okay. And there are preferred lines. There are special lines, the axes, right? Okay, so how can we reconcile this with Euclidean geometry? So the idea to introduce transformations into coordinate geometry that allow us to move any point to the origin and any line to the coordinate axes while not altering the geometry. So not altering the geometric quantities, we'll say. Okay. Well, but what geometric quantities are those? Ideally, right, we would want these motions, these transformations, to not alter length and not alter angle measurements, right? It turns out that specifying that they don't alter length is enough. You don't have to specify they don't change angle measurements, because you get that for free. Okay, so you get that automatically. Okay, and so what are these transformations? These are the isometries. So, definition of isometry. So, an isometry of the plane is a transformation that is a function, say f from R2 to R2, meaning it takes points in R2 to points in R2, such that if p sub 1 and p sub 2 are any 2 points, then f preserves the distance between them. i.e., so preserves the distance between them. That is a very important statement. What does that mean? It means the distance from f of p1 to f of p2 is equal to the distance from p1 to p2. Okay. Now, before we could define distance in this way, we needed coordinates, right? And so that's why coordinates allow us to actually give explicit constructions of the isometries. The Greeks were very aware of the different isometries and could definitely describe them and use them frequently. But having coordinates allows us to explicitly define these isometries, and it helps a lot. So, isometry, it's Greek. Iso means same. Metry means measure, distance, length. So same length. It takes points that have some distance between them, sends it to 2 points, f of p sub 1 and f of p sub 2, that have the same distance between them. Okay? And so it moves the plane rigidly, i.e. it is one of these rigid motions. So there's no bending, there's no splitting, there's no stretching. There's only movements that don't affect the length. Okay? And as we'll see, that also means they don't affect the angles. Okay, so all of the geometric things we care about are left invariant by an isometry. So that's an important word that we'll talk about. And so from this, if I use isometries, what this is saying is that I can move any point in my coordinate plane to be the origin via some isometry, and so the origin is really not as special as it seems. Okay, because this isometry is going to be nice enough that it's going to leave everything else fixed in a way that I can, if I have a picture and I don't like where that thing is sitting in my coordinate plane, I can use an isometry to move it to a place that I like. Alternatively, I can think of this as this isometry allows me to put coordinate axes wherever I want. Okay, so I can put coordinate axes at any point on a diagram that I choose. I don't have to just use the x and y axes, because an isometry will move any choice of coordinate axes onto the x and y axes if I want, right? If I've chosen the isometry to do that. So what are the isometries? So what are the isometries of R2? Okay, so let's go through a list. So 1, there are translations. Okay, translations might seem like the most obvious ones. Just move things around. Okay, so it's just a sliding, right? So a translation moves a point xy to a point x plus a, y plus b for some numbers a and b. So for some a and b that are real numbers. Okay. So the way that we write this algebraically is we have a transformation t sub ab is a function that takes a point xy and sends it to x plus a, y plus b. And it sends any other point similarly to, so if that other point is x sub 1, y sub 1, and it sends it to x sub 1 plus a, y sub 1 plus b. So it shifts every single point in the same direction by the same amount. Okay? Now, it's easy to check that intuitively you can see that this is going to be an isometry. It's not going to mess with the length at all, but let's actually just check that this is the case. So so here's my translation. So let p sub 1 be x sub 1, y sub 1. P sub 2 be x sub 2, y sub 2. Okay. Then what is t sub ab of p1? Well, that's x sub 1 plus a, y sub 1 plus b. And t of a sub b applied to p sub 2 is x sub 2 plus a, y sub 2 plus b. Okay. Okay, so let's check that this gives us what we want. So then the distance from t sub ab of p sub 1 and so the distance between t of a sub ab p sub 1 and t sub ab of p sub 2 is the square root of the difference of these points in each slot squared. So I have x sub 2 plus a minus x sub 1 plus a squared plus y sub 2 plus b minus y sub 1 plus b squared. All right. But of course, in each of these operations, the a's and b's cancel, and I'm left with the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. But this is the distance between P1 and P2. And so the distance between the transformed points is the same as the distance between the points originally. And so this is an isometry, right? That's how we prove that something's an isometry. Okay. All right. Okay, so translations form a very important example of isometries. What's another example? Rotations. Okay, now you might be like, whoa, this kind of sucks because we just got into a whole discussion about how angles are kind of nastier to deal with because we have to go through this whole process of talking about relative slope in order to actually talk about an angle. And so if I'm thinking about rotating about a point through some angle, right, so I want to rotate, so rotating about a point through an angle theta, that's it's a little annoying, right? That's a little annoying because then I have to get into that relative slope business. But actually, I really don't, right? So the idea is let c be cosine theta and s be sine theta, so that if I want to rotate through an angle theta, I have these two associated real numbers. And even if I don't have any nice way of coming up of expressing theta, the point is that cosine theta and sine theta, whatever they are, they're just two real numbers, c and s. But what's true about c and s? C squared plus s squared is equal to what? 1. All right? So c and s are just two real numbers such that c squared plus s squared is equal to 1, i.e. we can let c, s be real numbers that lie on unit circle, or whose coordinates lie on unit circle. So let that actually define c and s. What am I doing here? There. Okay. All right, so the rotation Now, we said rotating about a point here. We could start, of course, about the origin. So we could start about the origin. I'm going to barely cross that out. And the reason I'm going to barely cross that out, as you might have guessed, if I'm rotating about a point that's not the origin instead of the origin, how can I reconcile a rotation about the origin instead of a rotation about some other point? So I'll have you think about things like that in your next homework. So the rotation then, so associated to a rotation are these two real numbers c and s, such that c squared plus s squared is equal to 1. So the rotation r sub cs sends the point xy to the point cx minus sy, sx plus cy. Now, looking at that, it is not clear that that is actually a transformation, unless you're also in my 461 class, because we just did this a couple lectures ago. How if you wrote this out, you would see that, oh, it's a matrix product that makes it make a lot more sense than seeing it written like this. So then I have a transformation, right, that takes point xy and sends it to, in the first slot, cx minus sy, in the second slot, sx plus cy. Okay. Now, in order to see that this is actually a rotation, maybe we should actually look and see what this does to 2 points. So again, let p sub 1 be x sub 1, y sub 1, p sub 2 be x sub 2, y sub 2. From now on, that's when I write p sub 1, p sub 2, you can assume they have those coordinates using that notation. So then what is r sub cs, or what is, I should say, the distance between r, or actually maybe I should write out these things first. So r, no, I don't need to. I'll do it all in one go. So r sub cs of p1 and r sub cs of p2. Here, that looks. This is just r sub cs. Okay, of p sub 2. What is this? This is the square root of c times x sub 2 minus x sub 1 minus s times y sub 2 minus y sub 1 squared plus s of x sub 2 minus x sub 1 plus c of y sub 2 minus y sub 1 all squared. And what is that? It's going to be a really long expression. Okay, so this is c squared times x sub 2 minus x sub 1 squared. There's the mixed term, so that's minus 2cs x sub 2 minus x sub 1, y sub 2 minus y sub 1, plus s squared y sub 2 minus y sub 1 squared. And then in this second bit, this is plus s squared x sub 2 minus x sub 1 squared, plus 2cs x sub 2 minus x sub 1, y sub 2 minus y sub 1, and then one more term, plus c squared y sub 2 minus y sub 1 all squared. So all that's underneath the radical. Okay, and as it happens with these things a lot of times, the mixed terms cancel and allows me to simplify this vastly. I get c squared plus s squared times x sub 2 minus x sub 1 squared. That accounts for these two terms. And then lastly, I get plus c squared plus s squared times y sub 2 minus y sub 1 all squared. But both these are 1. Those are both 1. Why are they both 1? Because we said c and s are numbers such that c squared plus s squared is equal to 1. So both of those are 1. We're left with square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. But what is that? That is the distance from p sub 1 to p sub 2. Okay. And so, rotations are isometries, i.e., rotations in this way are isometries. Okay. Now you might say, is this actually a rotation, right? What does this actually do? So let's look at an example. Okay. So let's look at an example. What is R sub cs actually doing? Well, here I didn't break out my tools for this, so you'll have to use your imagination a little bit. Here's the origin. Okay, here's the point 1, 0. Here's the point 0, 1. And here, of course, is the point 0, 0. So let's apply R of cs to each of these. So what is R sub cs of 1, 0? Here, let's remind you how this was defined. So let me fold this a little bit. Actually, here, I'll just do this. So this is defined as cx minus sy. So this is c times 1 minus s times 0. And sx, so this is s times 1 plus c times y, so c times 0. Now what is that? All right, well, that's c times 1 minus 0, that's c. S times 1 plus 0 is s. So this R sub cs takes 1, 0 and does what to it? It moves it to the point cs, which we know lies on unit circle. Okay. All right, similarly, what does R sub cs do to 0, 1? So quickly then, this is c of 0 minus s times 1, sorry, c times 0 minus s times 1, and this is s times 0 plus c times 1. So this is minus s c. But where's minus sc? So this R sub cs takes 0, 1 to minus sc, which is here. Right? The same distance around unit circle as cs is from 1, 0. And then lastly, R sub cs of the origin 0, 0 is actually the origin. And so, like a rotation should, it would take the origin, since we're rotating about the origin, it would take the origin to itself. Right? Thus, this is exactly rotating about the origin. Through an angle theta, where c is cosine theta and s is sine theta. Okay. The default the orientation of a rotation is counterclockwise, so we'll say that this is counterclockwise, but won't get too much into that, why we don't need to worry about talking about clockwise specifically. That's actually already taken care of. Okay, and so this is actually a rotation. Okay, all right, so that's all the time I have for today. So we'll finish up chapter 3 entirely next time. So next time we'll finish up this discussion of isometries, prove the three reflections theorem. So I'll remove that from the description of this video because I included it. And yeah, we'll finish up chapter 3 on Monday. So anyway, we have office hours later today, and I'll send you a link when they're up. So hopefully I'll see you then. So remember, you have homework that's due tonight. So if you have questions about it, you can ask me in office hours. If you can't make office hours, you can email me, and I'll be on my email for the whole evening, basically. So anyway, I'll see you all on Monday.